So I'm going to start my presentation. Good morning, good afternoon, everyone. My name is Jiang, comes from Johns Hopkins University. So today I'm going to present our work on the topic of simulating disease spread during disaster scenarios. This work is the joint effort of Johns Hopkins and the University of Tsukuba. So about today's presentation, first I will go through our background, and then I will introduce a little bit about our base simulation model and our new proposed submodules. And then it will be, I will analyze the results from the experimental case study, and the conclusion part will be at the last. So in this work, we are considering the effects of masking and the large scale of evacuation on disease spread during disaster scenarios. So we also offer a map-based environment that enables analysis and simulation under various scenarios. So in this case, the analytical result from our simulator will provide decision makers with variable insights and guidelines for effective disease control measures. So basically, we are building our new features based on our previous work. So as you can see, this is our base simulator, which includes several submodules. So we are adding 2 new modules for the exploration of our new idea. So I will go through all of them one by one. So so as you can see, this is our base simulator, one of the submodules. It is the city representation. So as you can see from the figure 1, this is an example of the random view of our simulator. So we built it from the OpenStreetMap API, so we can depict the areas that really existed in the world. So actually, this is the University of Tsukuba and its surrounding areas. We also built various business institutes in the map, and we let all our agents to interact with those business. And this is the infection model. We basically modified the classic SEIR structure to have 4 different stages to be exposed, and 3 different stages of infection. But it should be noticed that we do not have the case from severe to dead. So which means during the whole simulation, we do not have any dead case for now. And we also have 2 different mechanisms for infection. It will be different inside the building and on the road. And for the agent model, we have different kinds of attributes. For the basic attribute, there will be something like walking speed and frequency of eating out. There will be some updatable attribute like hunger level and energy level. There will be some optional attributes like the health state comes from the SEIR model. And every agent will be assigned different kind of professions like office workers, off-map office workers, university students, and so on. So in this case, one agent is assigned different professions. They will have various schedules. So they will react differently under different situations. And we have the modular attribute, which is specifically designed for other submodules when the agent is interacting with them. And we have some attribute that is not used yet, like ages and genders. So currently we do not consider them as the factor that will have some inferences to our simulation system. And this is the behavior model. As you can see, we have some normal behaviors for the agent, like go to restaurant, go to work, go shopping, and sleep. And we have some behaviors regarding the infection states, like self-isolation or one step further, hospitalization. And we have some behaviors that are related to our new proposed model, evacuation and evacuated. So I will introduce them in the next slide. So here comes our 2 new proposed module. So the first one is the mask wearer model. Basically, we are assigning different mask states to the agent, no mask, surgical mask, and N95 mask. So different states will have different infection rate. And the statistics comes from the report of CDC. And on the other side, we are also building different intentions for the agent to change their mask behavior. So in this case, the mask states and the health state will influence each other in this case. The second model is the evacuation event model. So basically, we are considering a large earthquake scenario, in which case every agent or most of the agents will change their behavior and move to some nearest evacuation centers. So in this case, the behavior will be changed on the population level, and the disease spread will also have some influences. So we are going to investigate the disease spread on such a scenario. So the evacuation will be designed in 3 stages. The first stage is the start of evacuation. The agent will evacuate to one of several known evacuation centers. And during the evacuation, agents will remain in the evacuation centers until the evacuation period stops. And after the evacuation, agents will return to their normal routine schedule. So this is our new 2 new proposed module. So here comes the case study. So first is the experimental design. Basically, we are dividing our experiment into 5 parts with different combination of parameter setting of evacuation event and the mask wearing. But they have some general settings, like the simulation duration will be 10 days, and there will be 5,000 active agents with 10 who are initially infected. And the simulation area is University of Tsukuba and the surrounding areas. For the evacuation event, it will start at 5th day and ends at 8th day, which makes the duration is 3 days. And for the mask wearing part, the experiments 3 and 4, they will have some different subgroups that have different proportion of mask wearing at the initialization. But they will have no intention to change their mask wearing behavior. And for the experiment 5, we actually use this group to investigate the effectiveness of intention. So in this group, we divide it into 3 subgroups with low, medium, and high intention of changing mask behavior. So here comes the result part. So basically, these figures are the comparison of mask effectiveness among evacuation scenarios, and the conclusion of those figures will be similar. The high proportion of mask wearing will lead to a better disease control. But if you check the figure in the middle, it shows the growth rate of unaffected rate based on the growth of mask wearing proportion. So the growth rate is much higher under those with evacuation scenarios. It means that the mask is quite effective with those population gathering situations. And for this figure, it provides the changes or dynamics of mask wearing among on the population level. And it shows that high intention of agents to wear masks lead to a better disease control. And here is the analysis of the evacuation model. This figure is the real-time active location of agents, and it shows that most of the agents go to evacuation centers during the evacuation period. But as you can see from the yellow line, which is the number of agents on the road, and there will be some unusual increases in the number of agents at the start and end of the evacuation event. So this is the geographical visualization comparing without evacuation and with evacuation. The median-sized blue point is the evacuation centers, and it shows there will be lots of infection cases. And here you can see there is much more small-sized red point in the with evacuation scenario. So that is because those infected agents in the evacuation centers were spread out after the evacuation and keep infecting the surrounding area. So there will be a large-sized red point. After the investigation, we find out that this is a train station, and because our agents have some off-map workers, so they need to commute every day at this train station, which makes the infection event is very high. So here comes the statistical analysis of our model. So in the experiment, we actually repeated every parameter settings for 10 times with different random seeds. So, and we calculate the average and the standard deviation of uninfected rate here. So although we can find out that the standard deviation for those with evacuation scenarios is much higher than without evacuation, but it's quite low enough to say that we have a stable and reproducible simulator. So for a practical purpose, in order to provide convenience to our potential users, we build an analytical dashboard for interactive analysis and visualization. So basically, most of the figures you see in previous slides will be shown in this app. And also it supports to upload up to 3 data sets for comparative analysis. So now I will just give you several examples. So this is the dynamics of infection rate. This is for the mask wearing intention comparison. And here you can check a single agent's behaviors categorized by the stages of their infection. So in this case, you can observe every single agent and just get the intuition about how our simulation is working. So I will just wrap up here. We are building a multi-agent system that examines various scenarios of COVID-19-like disease transmission in a small community level, and we are considering different mask usage and evacuation conditions. So in the experiment, we show the stability and the reproducibility of our simulation, and also we provide a flexible simulation because the user can customize their own disease model, their own disease agent model, and the city representation, and so on, to fit their own scenarios. So such a simulation would provide a great practical purpose as a real-world application. In this case, the policymakers will get some potential ideas from the simulation result and perform better disease control measures. As for our future work, I think we have some exciting directions, like we might want to add emotions to our agent, and we're going to let our users to easily replace their simulation map. And we are not only just considering about evacuation events, but also some other various events. And we can let multiple disease function at the same time. So I think in the future, we can get our simulator more completed and more informative. Also, we have our open sourced public repository, so you're welcome to reproduce our result or customize your own simulation and get your own result. So thank you very much. That's my presentation today.